To help everyone understand, I made some of my own. I started by creating a canvas that I could display the information with. From there, I created an image object that holds color and transparency information for each pixel. I then iterated through each pixel, getting its X and Y position. Using that information, I mapped the pixel to a number depending on the current position and scale. For now, let's assume that the scale and position is set to their defaults, where the pixel at the top left represents -2 plus 2i, the pixel at the bottom right represents 2 minus 2i, and every other pixel represents something somewhere in between. We can then plug in those numbers to the Mandelbrot set function, z equals z squared plus c. We then do this over and over again a certain amount of times, which we call the number of iterations. During each iteration, we can determine if a point is in the Mandelbrot set by checking if its distance from the origin is greater than 2. If the distance is greater than 2, the number is, for sure, not a part of the Mandelbrot set. If after the decided number of iterations is reached, and the point's distance from the origin is still less than 2, we can assume that the point exists within the Mandelbrot set with an accuracy decided by our number of iterations. The higher the iterations, the more accurate the Mandelbrot set gets. As the number of iterations increases, the border of the shape becomes more and more detailed. To color the Mandelbrot set, we can use the number of iterations that it took for the point's distance to become greater than 2, if at all. If a point never reaches the threshold, we color its corresponding pixel black, signaling that it is part of the Mandelbrot set. If a point was super close, just one iteration away from being in the set, we color that point a vibrant green. If the point is 2 iterations away, we color that point a slightly less vibrant green. As the point gets farther and farther away from being part of the Mandelbrot set, the color of its pixel becomes less and less vibrant, eventually reaching black. Now that I've explained how I made this program, I'll explain how to use it. To zoom in, click the point that you want to see further into. This will shift the center of the view to your cursor position and zoom in a bit. If you've found that you've gotten off track, click the Reset View button. To change the number of iterations, either type the desired number of iterations into the box, or click the up and down arrows. To change the color of the glow around the Mandelbrot set, either drag the sliders to the left or right, or click the Randomize button to get a nice surprise. I've spent far too long messing around with it. And that's it. I hope you have fun messing around with my program as long as it's up. Okay, you've made all these cool flashy things, but is there any practical reason for fractals, you say? And my answer is, kinda. There isn't any practical use for the Mandelbrot set itself. That's just for show. But there are some uses for fractals in general. One of these uses has to do with data compression. Although fractal compression is really complex, nothing that I'm capable of doing anytime soon, I can share the gist of it. An image is converted into something called fractal codes, a long list of numbers that describe the image. I don't exactly know how they're made, but fractals help the generation of these lists. This approach takes advantage of the fact that images generally have parts that resemble different parts of the same image. Sadly, this method only works for black and white images and involves a good amount of lost detail, so it isn't too useful for everyday life. Nevertheless, it's still interesting. That's all I have to say. I hope you found the world of fractals interesting,